This afternoon we have Ike Muller, who's from Bath University, talking to us about elliptic solvers.
Okay, thank you. Yeah, so I'm going to talk about elliptic solvers on GPU, so probably I should rather have called the talk one elliptic solver, one GPU, but there will be some, no, I mean, we started looking at multiple GPUs and going from this one solver, we're looking at two other solvers, I think is not a big step either. So this is work which originally started off as Sinan Shi's MSc thesis. So he did MSc at the Edinburgh Parallel Computing Centre this summer. And he finished in August, and since then we've made quite a lot of progress. So I showed some results. Well, he contributed a very important idea, and in the last few months we did some more runs on our new GPU computer in Bath. I've shown some results already at the meeting at the Met Office. We'll show them again, but then, as I will show you, we've done a lot more since then. Okay, so why am I talking about elliptic solvers and why am I talking about GPUs? Well, you probably all know why solving elliptic PDEs in numerical weather and climate prediction is important or can be important. And well, the reason is that if you do semi-implicit semi-Lagrangian time stepping, you can do a larger model time step. So that's good. But on the downside, you have to solve a global elliptic PDE for the pressure correction every model time step. And there is kind of that is often a bottleneck in your implicit code, and there's also kind of a perceived notion that this limits the scalability of the model. Okay, so I'm not talking about scalability today, but what I will talk about is about performance. So the model resolution is, well, in Gang Ho we're hoping to go up to maybe a few kilometers, so the number of degrees of freedom will go up to more than 10 to the 10 degrees of freedom. And at the same time you want to keep the wall clock time to solve the forecast model fixed. So that means you need a really fast and also scalable solver for elliptic PDEs, and nobody really knows what the hardware will be in 10 years. So that could be, it's probably something which has lots of cores, but it could be a CPU with lots of cores. It could be something like this Intel Mic processor, and it could also be a GPU. So that's basically the reason we've been looking at that. Yes, so here's an overview. First, as a motivation, just to remind you why we're actually looking at GPUs, what's the good thing about GPUs, and how do you program them. Then I want to say a few words on the model equation we've been looking at. And then in the main part of my talk, I will talk about this Q-C implementation of this preconditioned conjugate gradient solver. One thing that we discovered in Sinan's thesis is that the memory layout is very important. So that was an important lesson we learned there. And he looked at quite a simple model problem, but we've now done a more realistic model problem, which is actually the same that I've been using for all these scaling tests on Hector. So that's just this model on one panel of the cubed sphere grid. I will show you some results. And then also last Friday I implemented this new, well, it's still the conjugate gradient algorithm, but Rob had an interesting idea how you can reduce the memory access in this algorithm by moving some of the BLAS operations in with the kernels that you put on the GPU, and actually that gives you that's actually quite important because memory access is important. And then, as I promised, so there is a bit on multiple GPUs in my talk. I will say something about, Rich Loft talked about this shallow water model that Lin Gan coded up, and he talked about this at the Met Office. So I will just briefly say what he did, and then I also did some first just measurements just to see how important, how does this data transfer between the host and device, between CPU and GPU, does it actually kill us, or is it maybe not so bad as everyone always says? So I got some results there in the last few days, and then I just conclude. Okay, so why are we using GPUs and what are GPUs? I mean, GPUs are graphics processing units. They have a large number of relatively simple cores. So this is just to give you the idea. So on a CPU, you have a lot of cache, you have a lot of control units, speculative prediction and whatever, and then you have some floating point units as well. On the GPU, it's the other way around. So you have lots of quite lightweight cores and only very little kind of cache control and other stuff. I mean, that's there is on these modern GPUs, there is also cache, and so that is changing a bit. But the important thing is that you have these simple cores. They're usually on quite a low clock speed, so 1 gigahertz, maybe 1.3. So that means these GPUs, they're very power efficient, and that might actually be the thing that will convince people in the future if you can actually run your supercomputer on much less power. Yeah, there is a hierarchy of memories. So there's some global memory, then there's also shared memory and constant memory. You can use that to make your code faster, and you often have to do it by hand to get the optimal performance. Again, that might change. It might become more automatic. The other thing is, it's not only the sort of the flops that are that you can't only push through more flops on a GPU. Also, the memory bandwidth is larger. It's a factor 4 or 5 larger than on the CPU. But what is still expensive is getting data onto the CPU. So obviously your code first sits on your data sits on the CPU, and then you have to get it on the GPU. So you want to avoid that if at all possible. And I will say more about that in the end when I talk about these multiple GPU implementations. Okay, so this is just some pictures from NVIDIA. So this is just kind of the flop rate of several GPUs. So this is so these are different cards, but I think this is the Fermi architecture here, and then the Kepler that came out this year or is coming out soon is up here, and the CPUs, they are sitting down here. So the flop rate of these GPUs is much higher, at the order of teraflops, and also the peak memory bandwidth is significantly higher. So the runs I did were on this Fermi GPU M2090, which is also the same as this Emerald cluster Adral has. So that's why we decided to use this. This is very recent. I think it came out last year. It's 512 cores, peak performance 1.3 teraflop for single precision and 0.6 for double precision. The peak bandwidth is around 180 gigabyte per second, and I also measured the bandwidth for transferring data between the host and the device, and that's significantly lower. So that's just about 1 gigabyte per second. Yeah.
That one sounds very low.
Yeah.
Yeah, PCI Express should be capable of more than that, right?
That's what I measure.
Okay.
It should, yeah. Okay, I can double check that, but yeah.
Typically, the quoted number for PCI Express to 3 is 16 gigabytes per second.
16.
If you're measuring it, you're not going to saturate
Yeah.
the peak.
You're not. Well, it depends what you measure it with. But but I mean, that's 0.1 of peak, which if you were just doing a straight mem copy over a non-busy machine, you hope to get a lot more.
It's like about 10%.
Yeah, 0.1 of peak. Yeah.
Okay, yeah.
10% of peak.
Hmm.
Well, if you were just doing a straight contiguous memory mem copy on an unloaded machine, you'd hope to get a lot more than 0.1 of.
Okay, but even if it's 16 or something,
It's small.
It's small. Okay, so then this is the latest Kepler GPU. Yeah.
Did you measure it for your algorithm?
Yes.
Because that's not contiguous. It's not contiguous in
No,
memory.
no, it is.
It's contiguous
Yeah.
in memory?
Well, what I do, I will say something about this later. Part of it's contiguous, the other bit I make contiguous and then unpack it on the GPU. So that's what you have to do. So there is some additional cost. On the GPU, yes.
So the first 3 numbers in here are guaranteed not to exceed numbers, and the last one is your actual digit number.
Yeah. Again, these are very recent results, so there might be a factor 5 or something wrong there. Okay, so this is the Kepler GPU that came out this year. This has even more cores. even better floating point performance, and the bandwidth is also increasing. Good. So yeah, the programming model you use on GPUs is a bit different to what you do on a CPU. It's basically, well, a vector machine, I would say. So what you have is, what you do is you always isolate your compute-intensive subroutines in simple kernels, which are only a couple of lines long. And these kernels should be able to execute independently. There shouldn't be any communications, there shouldn't be any fancy if statements and things like that. And then you have this kind of single instruction multiple thread execution model. So what the GPU basically does, it executes all these kernels in parallel. So each core does exactly the same instruction at the same time. And it organizes these threads in a block. So there's in a grid. So there's a grid of blocks, and each of these blocks executes on one of these streaming multiprocessors, and on one of these streaming multiprocessors there is this grid of threads, and these are then executed in parallel on each streaming multiprocessor. And the nice thing is also you can hide the latency, because what you usually do, you submit more threads than the GPU has cores, and whenever one of these threads or thread blocks can't do anything because it's waiting for memory, it just takes the next one, which already has its data, and keeps running with this, and by that time the first one got its data, and so on and so on. So you can hide the latency, but you need a lot of threads, so that's the caveat, which might be an issue for strong scaling, obviously. Okay, and then here's just an example. If you do a 2D matrix addition, so you just take some matrices A and B, two-dimensional matrices, and you calculate Cij. So what you do is you write this kernel, which I call mat_add, so it gets some A, B, and C arrays. And then each of these threads just calculates its index, I and j, from the block index and from the thread index inside this grid. And then each of these kernels just does this operation, this just summation of this one index. So this is an extremely simple kernel. It can be a bit more complicated. In our case, it was more complicated. Okay, so now I'm going to say a bit more about the model equation we're actually solving. I don't want to say too much because I've mentioned this so often in other talks. So basically, we're looking at this equation for the pressure correction in semi-implicit semi-Lagrangian time stepping. What we came up with is this equation here. So you have some second order derivative in the horizontal direction, and then you have also second order derivative in the vertical direction. And you have a constant term, and there are some constants here. There's an omega squared in front of these derivative terms, which is basically given by the size of the time step and the speed of sound waves in your model. And then you've got this lambda squared here, which is given by the buoyancy frequency. So this is kind of the simplified equation we came up with last year. And you want to solve this in some spherical shell, which represents the Earth's atmosphere. And one of the important things about this equation is that because the vertical grid spacing is much smaller than the horizontal grid spacing, you have this very strong vertical anisotropy, and you can use that to construct a very efficient preconditioner for your solver. We are actually solving in, we are able to solve it on the sphere. But we are, this work was done on one panel of this cubed sphere grid so far.
Does restricting it to one panel, does that change the condition of the problem significantly?
The condition?
Number of the matrix that you're trying to invert?
No.
Hang on. Isn't the... Oh no, this is compressible, right? Yeah, no, that's true.
It's not Poisson, it's
yeah. If it was incompressible,
the nice thing is that you have this term here that helps a lot with the multi-grid solver.
And the delta 2D doesn't really help.
And with the ZG as well. Helps with everything.
Well, yes, but not so much, I think.
But if it wasn't there, then the ZG solver would really have trouble.
Well, this term isn't so small. This is not so small, so.
You just said the U term, no?
Yes.
If the U term is not there, then you have a Poisson equation.
Mm-hmm.
And it's badly conditioned. Then if you make the problem bigger and bigger, it will get worse.
Oh
and
yeah,
worse.
yeah, no, I agree on that, definitely.
More of the point
yes.
of the Poisson equation, it's as you make it thinner, it gets worse.
Mm.
And therefore having only one panel as opposed to all 8 of them is relevant, but it doesn't matter so much here because of that nice U on the end that forgives many sins.
Yeah, I mean,
Six.
Sorry?
6 panels.
6 panels. So in the Poisson equation, information transmits at infinite speed. And so the bigger the domain in that direction, the worse life gets. Whereas in this problem, information propagates at finite speed, effectively. And so it no longer matters that you keep making it bigger.
the important thing is also that you scale this omega squared, well, you scale the delta t with the delta x. And then actually the condition number doesn't change as you increase the resolution. But that's probably what you mean, that it actually helps with the CG solver as well. Yeah. Okay, so what Sinan did in his MSc thesis is look at the simplified equation in the Cartesian box. So we just take the same equation, but we left out this kind of curvature, this derivative in spherical coordinates, and just replaced it by an ordinary derivative. And we use a finite volume discretization, and then we obviously get linear algebra problem. So this matrix vector equation here, which we have to solve, and the matrix looks like this. So when you write it down, you have these. So you have these, well, obviously you have a diagonal, and then you have these red terms, which are the couplings in the vertical direction, and you have these blue terms, which are the couplings in the horizontal direction. And the way I wrote it down here, I basically used a numbering of the degrees of freedom where the vertical index runs fastest, and that's obviously what you want to do on a CPU for cache efficiency. So that's a good idea. And then this matrix basically decomposes in these blocks. And what I said before is there's a very strong vertical anisotropy. So the ratio between the horizontal coupling and the horizontal grid size and the vertical grid size is large. So this gamma here, which basically sets the size between this term and this term, is very large. And then actually a good preconditioner is one where you just drop this term here and just take this term, and then the matrix just decomposes in these dark gray blocks here, and just becomes block tridiagonal or tridiagonal matrix, which you can invert very easily using on each horizontal grid point by using this Thomas algorithm. And that's this block diagonal preconditioner we use. So yes, the solver we used is a simple conjugate gradient solver. So I just wrote down the main loop here. The important thing to remember is that there's kind of 2 or 3 kinds of operations. We have to apply the matrix at some point. So this is this operation here, which is just a matrix vector multiplication. And we have to apply the preconditioner once in each iteration. So we have to solve the system mz equals r, where m is this block tridiagonal matrix. And then we've got some other operations which I've written down here in green, and they are kind of BLAS level 1 type operations. So you have this AXP operation, so you add something to this vector uk, or you do some scalar products, or you calculate the norm or whatever. So these are the operations in green. And it actually turns out that most of the time is spent in the apply function and in the preconditioner. So that's one of the first things Sinan did. He just timed the CPU code, and he found out where the bottlenecks are. Not very surprising. Surprisingly, it came out that it was this apply function and this preconditioner. And what he did then, he developed a Q-C implementation. So and the point is, we did it in a way where we never transfer data inside the CG solver between the host and the device. So we store all the data on the GPU and do all the calculations on the GPU. So for the BLAST operations, we just use this QBLAST library, which is just a NVIDIA CUDA library, so that was very easy. And for the kernels, we use this, what we call matrix-free implementation. So what we basically do, we never actually store this matrix A here, but we always recompute it. So for example, if you do this matrix apply, you have to get X at the same position ijk, and then you have to multiply it with the diagonal matrix element, which we recompute. Then you have some off-diagonal matrix elements and so on, but we always recompute them. And actually, for the simple equation he looked at first, these expressions are very simple, so calculating them doesn't cost anything. However, we also did, as I will show later, we also used more realistic coefficients here, and still it turns out that this matrix-free implementation is actually a good idea on the GPU. Okay, so for the apply function, it turns out you can actually use one thread per three-dimensional index, because these operations are all independent. For the preconditioner, where you have to do this tri-diagonal solve at in each vertical column, we used the Thomas algorithm, and there you have a dependency in the vertical direction. So you can still do all the horizontal grids, all the columns independently, but in each column you have to you have to process each column on one thread. So there we did just horizontal partitioning. So the other thing to keep in mind is that all these operations are dominated by memory access, and that doesn't really change that much if you put in more complicated coefficients, because you have to load 7 vectors from memory and you have to store 1. So, and then you have some flops here. Okay, so that's what Sinan did, and he did it on this Hector GPU testbed, which has slightly different GPU. This is a bit slower than the one I did for these realistic runs. And he got, for the apply method, he got quite a good speed up of 20 times, of a factor of 25. That's relative to one thread on the CPU. And for the preconditioner, he got a not very good speed up. So he did some optimization there. He did some shared memory optimization, but he only got a speed up of 3 to 10, which is not very good, because the CPU also has, I don't know, 10 or 16 cores. So it's probably, well, the GPU isn't much faster than the CPU if you do some OpenMP on the CPU.
What was the CPU?
Oh,
Hector.
I don't know, Hector.
The credit.
Yeah.
This was the GPU machine, so the strict speed was not the credit. They still got an AM, some flavour of AM in it.
Yeah.
So fairly similar to what's on. I don't know if it was in the Lagos, but it's similar. If it wasn't, it's probably making calls.
This is not the end of the story.
No.
It's giving a historic talk.
Yeah.
This is a bandwidth limited operation, right?
Sorry?
You've argued previously this is a bandwidth limited operation.
That's right.
So 25 is too high, right? You don't have 25 times as much bandwidth on a GPU as you do on a CPU. So if it really was a bandwidth limited operation, that would indicate there was something wrong with the CPU implementation.
That might well be.
Sorry?
So
I don't think that there's something wrong with the CPU, because you're gonna get to factor 100 afterwards. Then our CPU thing would be seriously wrong.
CPU, so if you're going 100 times faster on a GPU than a CPU, then A, you're memory RAM, and B, it's still suspicious, right? There aren't just the CPU's guarantee. If you go back to this first slide with the guaranteed not to exceed performance numbers, they just are not 100 times higher than the ones on the CPU. So
yeah, but whenever you write GPU code, you're restructuring what you're doing anyway, so you're not doing exactly the same thing. So
you're not doing exactly the same thing, but at the end of the day, the underlying algorithm has flop counts at scale in not radically dissimilar ways. So, like, I don't think there's a flop saving operation in here. So it doesn't really line up with the properties of the hardware for that to.
So what would you expect? You would just expect a factor of 4 or 5.
That seems not completely unreasonable.
But if that's true, then there's no point in going to a GPU at all, because
well, you've got to remember that you don't necessarily, if you're memory bandwidth bound, that memory bandwidth doesn't multiply up from the CPU. So when you use all the cores, you don't get...
Yeah, but the initial speed up is against just the serial code.
Yeah,
which is the
exactly.
right answer.
That is probably the point.
The serial code just is correct. That's it. There's nothing else to it. There's no optimization in it.
Well, in that case, it's not meaningful to put up multipliers.
Indeed.
Multiples.
I don't understand
So
that,
the
because
interest
if I take the CPU code and I give you the sequential code, and then I say if you now parallelize that in your optimal way, the most you're going to get is factor 16 if you've got 16 cores. So all you need to do is take the number we're going to give you, divide by 16, and that's your optimal speed up that you, or the worst speed up you could get versus the CPU.
Except you haven't got an optimal cache-based code, and you might get better access on that. And usually what you find is when you rejig your code from GPU, you rerun it on your original machine, you get much better performance. So a lot of there are these rules that people have about bad comparisons, and that's one of them. You know, you need to at least compare restructured code.
It's also...
That's what we did later.
So that's a restructured one.
But also when you talk
original.
about memory bandwidth limited codes, you've got to remember that you can't just multiply back out the CPU one by the number of cores. Because you don't have... So when it says you've got 40 gig per second bandwidth available in your CPU, that doesn't mean that your 6 cores have 240. They don't have 4
but all I'm arguing is this is going to be disfavorable for our GPU factor, because if you're telling me that you cannot get the factor 16 out of 16 CPU cores, then our number is going to be even more favorable for this GPU.
Why don't we just read x as some arbitrary unit of speed and move on?
Yes, I mean, this is actually not my point here.
Okay.
So I think we should probably argue about this after I showed you my final results. Well, my point here is really that for the apply function, he got a very good speed up. For the preconditioner, where you have this vertical dependency, he didn't get a good speed up. So this is a really poor speed up for a GPU. And the total speed up was also in this order of 3 to 10 or something.
You need different lines, different kinds of speed up?
Oh yeah. There was also, right, that's something we dropped later. We also did an SOR preconditioner where you have an additional apply there. So probably just ignore this. This is just a plot I got from his thesis. So you want to look at this one.
Blue solid lines are really interesting.
Exactly, yeah. That's one, it's the blue solid lines. And the red solid ones. Okay, so, and the reason this performance was quite poor was actually related to the memory access pattern on the GPU, because what happened is that these threads are always scheduled in warps of 32 threads, and they always access memory in a coalesced way. So basically what happens, we have got the number of threads here, and they move up, they execute the Thomas algorithm, so they move up these vertical columns here, and in the first step, they all execute the same operation, they all need this data here. And if you do it using the Z-aligned, which I call the Gang-Ho data model, it just means you store the vertical columns together, that's all it means. If you do this, then actually what happens, the threads don't access coalesced memory. So the first one reads this one here, the second one reads this one here, and so on and so on. So the memory access is really not coalesced at all. And that's not a problem for the apply function, because there you can just basically repetition but there you can do this 3D petitioning, and that's not a problem. They just align them in the vertical direction. So, but for the tridiagonal solve, you can't do this. And the solution to this problem is very easy. All you do is you just change the memory layout. You don't store vertical columns consecutively. You just store horizontal columns consecutively. And if you do this, then the memory access is perfectly aligned.
It's kind of tricky to do in unstructured mesh, right?
Yes?
You do have another alternative, actually, which is something we did when we went on to GPUs for the assembly problem. It's the same problem here, which is you don't have to use the threads in your thread book the same way for fetch and solve. So what you can do is you can get your threads to gang up and fetch each other's data in a coalesced way to get your tridiagonal systems. And then they flip round the other way and execute them. But now they're executing from the shared memory buffer, and so therefore they don't care about coalescence anymore.
Okay. The shared memory is only limited size, so you have to use.
Right, but you're talking about fairly data light operation, right? If you just got the 3 numbers in a tridiagonal solve, then that's not so bad.
Okay.
So I heard that you don't have to be contiguous, you just have to make sure the modulus is right, so that you overlap. Is that something you've heard as well? Or?
I'm not so sure. I mean,
Well, I would actually say that that's what my comment constantly was to him. What he is showing with the X numbering isn't contiguous. It's only what you're saying. It's only, what did you just say?
I said modulus.
Yeah, because if you've got more than 16 cells in the X direction, you actually need the next 16 values of the next row already to do your Thomas algorithm. So you actually should order them in terms of multiple streaming processor sizes, and not in terms of the whole X row.
well, that's probably true, but it depends on the block size as well, I think.
Well, all I'm saying is we are ordering it in X first, then you're still jumping, because the next thing you need for the algorithm in the first 16 columns is the thing that comes in the next X row, which is it's not contiguous in memory. So it's only at least modulo.
Okay.
I think so.
I mean, my point is really that if you do this, then you get a dramatic change in performance. So I mean, once he did this, he got much better speed up. So for the apply, it was better, and for the preconditioner, it also went up to 41 times now, not 3 to 10. And the total speed up is 34. So these numbers are very preliminary, and that's numbers I got. So I have more on the following slides, but it was the first observation that we made. Okay, since then we looked at a more realistic model problem, and we put in this kind of curvature term in the vertical derivative. And again, we use a finite volume discretization, and now we work on one panel of the cubed sphere grid, and we also use the grading in the vertical direction. So the grid levels in the vertical are not equidistant, their distance increases with height. And we also, in addition to this matrix-free code, we used some matrix-explicit code. So the point in the matrix-free code is that we never store the matrix, we always recompute it. And we also basically wrote some code where we store the matrix. We calculate it at the beginning, and then we just need to load it from memory. And this we implemented using existing libraries to get the best performance. So we use compressed sparse row storage for this, and a preconditioner you can still basically you can still use this tridiagonal solve, but you have to do it over the entire domain. It's still a tridiagonal matrix, but you don't do it blockwise. You do it for the entire n times n matrix. Well, the reason why we think that this is not such a good idea is because you have much more memory access if you do this. So in addition to the vectors, you also have to load the 7 stencil entries in the matrix supply when you load the matrix. As a matrix-free code, we just calculate them. We never have to load them.
You have to load the things that you need from the calculator.
Yes, that's right.
So why is that a win?
That's like 1 or 2
But
numbers
yeah,
for the whole
it's much
column.
less. And you can keep that in registers and cache.
If your vertical quality depends on previous time level, which it does in endgame, I think, you're still going to have to load a 3D field each time to compute a matrix.
Yeah,
So
that's
yeah,
the question.
Yeah.
But I mean, you have only got R-dependent fields, no? Or is that right? Okay. So that was also an assumption in most of the CPU work, which we need to study.
Okay.
Please continue.
The other thing in this approach, in this matrix explicit approach, is that you have to set up the matrix in the beginning. So this might be some overhead which you can avoid in the matrix.
Yeah, there's a whole literature out there about people working out how to do that on GPUs, right? In particular, Andreas Drucker has done some clever stuff.
Okay.
Because you're right, the straight CSR insertion problem hurts, and GPU is not a nice operation.
Well, I'm not claiming that we're using the fastest one. We just use.
But you need
some.
to build it somehow. Even if you're doing
Yeah.
it with the fastest one, you need to build it.
You do need to build it out.
Okay, so this is just how we implemented it. So for the matrix free one, obviously we wrote it ourselves on the CPU and on the GPU. The matrix explicit one, we used LAPAC on the CPU, and the CSR apply I actually wrote myself. And on the GPU we used this QSparse library, and for BLAS we used, on the CPU we used GoToBLAS, and on the GPU we used this QBLAS library as we did before. So there's no difference between matrix free and explicit here. Hardware is, well, for the CPU we used the Sandy Bridge processor, which I believe came out this year. So it's still sequential code, but this node in Bath has actually 2 × 6 cores. Clock speed is 2.0 gigahertz, and the peak bandwidth is around 40 gigabyte per second. And for the GPU, we use this Fermi card here, which is 512 cores, and peak performance is around teraflop, and it also has 6 gigabyte of memory.
What is that 42.6 gigabytes a second number that you found with over?
Sorry?
So
Right,
is that what
The whole socket?
is that what both sockets have? Because that's a 2-socket system, right? So is that what each socket has to its adjacent memory bank, or is that the sum of those two, or?
That I don't know. Okay, for the host device bandwidth, as I said, I measured 0.9 gigabyte per second. Just for comparison, the MPI interconnect on Hector is 5 gigabyte per second. But we had this discussion before, this might be rather 10, 60. So
Is the second number also measured, or is that?
that's from the web page.
That's notional.
Yeah. Okay, so here are some results. So this is now really the kind of the final code with the full problem. So what I show here, so on the right, on the left, there's the matrix explicit code. So the light colors are always on the CPU, and then I show the GPU results in these dark colors here. So you see that, and this is a logarithmic scale on the vertical axis. So for example, for the apply method, the GPU code, the matrix explicit GPU code was 26 times faster, and for the preconditional it was 16 times faster. So this is the matrix free code on the right. So that's an interesting observation we made. If we, the matrix free code on the CPU is actually slower than the matrix explicit code. That's something I haven't really understood yet.
Does that mean that you're not actually bandwidth limited? Because the one on the left definitely has a lower flop count.
Yes.
But how could that be? I mean,
I'm surprised. Don't worry.
Yeah,
It's a low order method doing something really simple.
exactly.
My gut feeling says it should be bandwidth limited, but then if it's bandwidth limited, then the matrix free one you expect.
You're right.
You need to do.
You're not accidentally doing something horrible with cache.
Well, I mean,
Yeah.
Smashing it to death.
well,
that's
Something's
what we
going on because
thought
those
was
two
that.
numbers on the end there are not believable, right? So if you go back to the previous page, you've got, if it's memory bandwidth limited, you've got, depending on which one of, exactly how we interpret those numbers, the guaranteed not to exceed memory bandwidth on the GPU is either 4 or 8 times the guaranteed not to exceed number on the, sorry, it's either 4 or 2 times the one on the other side.
The matrix explicit on the CPU is using GoToBLAS, and the matrix free is hand coded, right?
No.
no,
they're
this
not
has
the same
nothing
class.
to do. There's nothing to do with glass. What I can say, that's another observation. If I don't switch on any optimization, I don't see this. So I only see this. This only shoots up if I do minus 0.3. So if I
So when it shoots up, I thought the other one shoots down. Well,
okay, well, relatively, the matrix explicit one becomes faster. Yeah, sorry, yes, this one goes down.
I
Yeah.
hope that the optimization doesn't
No.
work.
No, that's right. So this one goes down. So if you just do
actually,
O0,
03 you can go worse. It's kind of what 03 means. 03 is unsafe. So for most compilers, I don't know which compiler used it. For most compilers, 02 is everything that the compiler vendors expect will always be better, and 03 are things which may not be better, depending on what you're doing, because it's not always obvious. Or incorrect.
Can I ask you, Rupert, and can I ask you, both of you, what is, you're always talking about this memory bandwidth, this theoretical thing, which I understand in a theoretical sense, but if I'm actually running code, and I'm actually comparing just what I measure from the start to the end, how am I ever gonna know that I'm fully 100% memory bandwidth bound?
So one answer is that you can, you see, especially on a CPU, especially on a GPU, where you can kind of prove what the code does, which is much harder on a CPU. Then you can actually calculate, you can model how much data your problem should be loading. And so therefore you can work out how much data you've actually moved, and you can divide that by what the manufacturer says you'll never exceed. And so you can do a similar stuff for CPU, so that's the whole performance modeling game. So when you see a paper which says we hit blah percentage of peak, that's what they've done. They've calculated how many flops they did, they've calculated how long it took them to do it, and then they've divided that by the theoretical maximum they could have ever achieved.
yeah, and that's on my next.
Ah! Do you want to show us the next slide?
There's another one before that. So this was single precision, and one of the things Richard Loft said at the Met Office is that people always only show single precision, and that's kind of cheating. But we also did double precision, and yeah, that's the results we got there. Oh, one thing I haven't said on the previous slide is, so these black numbers are always the speed-ups relative to the CPU code. These white numbers are the speed-ups of the matrix-free code relative to the matrix explicit code. So here we find this is 1.7 times faster than this one for the apply function. For the preconditioner, it's a factor of 3 times faster for single precision. So these are the double precision numbers. There the preconditioner is even faster than the matrix explicit one, and the apply function also. Yes, okay. Good, so now that's what David just said. These are just very rough estimates. I'm not claiming they're very accurate, but what I did for the applied kernel, I just thought about how much data do you have to load and how much do you have to store in the applied kernel. You have to load 7 vectors because it's a 7-point sensor. You have to write 1 vector back to memory. And the size of the problem is 256 times 1 to 8. So for single precision, it turns out we have 0.268 gigabytes, and it takes 4.14 milliseconds. So if I just divide this by the peak bandwidth, I get 37% of peak. For double precision, it's twice the amount of data I move, and it's slightly slower, and I get 71% of peak. So again, that's something I don't quite understand, because why would it be so much better for double precision?
Maybe because your coalescence is not as good as you might like to think.
Yeah, that might be true. So what happens? It always fetches, I think, 128 bytes.
Right, so
and
it's
that
easier
doesn't
to do it in
change.
double.
Yeah,
It's easier
that's
to...
right. That
Yeah.
might be it. Yeah. Okay.
I don't quite understand the 1 vector and the
1.
7. Why is there load 7 and 1 stored?
Well, you have to load x 7 times and write y back once.
This is the
Understood.
This is the pre-computed matrix.
Matrix. This
No.
is the matrix applied.
It's the matrix free one.
This is matrix.
Yes, and for if you do it matrix explicit, you have an additional.
Is this a
7.
directly addressed mesh?
Yes,
Okay.
it is.
But some of those, but you get some reuse because
So
you're reusing some of those vectors as you go.
yes, so they might be stored in cache, but how exactly is I don't
It's
know.
hard to understand.
Yeah. So that's why.
Sorry, Ika, can I suggest we let Ika get to the end of his talks? We're running out of time fast.
Yeah.
Ika's got a lot of slides to go, and then there's time for discussion afterwards if people want to stay.
Okay, so I did the same exercise for the flop rate, and this is a rough estimate. I estimated 100 flops per grid cell as an order of magnitude for the more complex problem. And then for single position, I get 15% of peak. For double position, I get 30% of peak, if I just make this calculation. Okay, so this was just for the individual bits, for the apply function and for the preconditioner. But now looking at the total solution time, so again, this is matrix explicit here and matrix free here. And again, the light colors are on the CPU, and then I've got the GPU code. And what you see that for the matrix explicit code, I get a speed up of around a factor of 10 or 8, depending on whether I do single precision or double precision. And for the matrix free code, I get significantly larger speed ups. Part of this is because the matrix free code is slower on the CPU, so actually you would have to take that into account to make a fair comparison, but just assuming that. Then I also again calculate the speed up of the GPU matrix free code relative to the GPU matrix explicit code, and again I get these factors of 2.7, 2.9, so around a factor of 3. Okay, so these times they included matrix setup costs, and what I did for the matrix explicit code on the GPU, I copied the entire matrix across, which is not a good idea, because what you really want to do is you want to set up the matrix on the GPU. And to avoid counting this, I just looked at the time per iteration. Again, matrix explicit, single and double, matrix free, single and double. And then it turns out you get better speed ups for the matrix explicit code. So it's a factor 18, 11 here, and well, for the matrix. And then we only get a speed up of around a factor 1.8 of the matrix free relative to the matrix explicit code for the time per iteration. Now, it's interesting to actually look at where this time is spent. So if we look at the matrix explicit code, then there's obviously the apply function and the preconditioner, and that takes up most of the time. This is for single, this is for double precision. For the matrix free code, it's not so clear. So in addition to this apply and preconditioner, you have all these blast routines that we do with this Q plus. And if we look at the matrix free code, they actually make up almost a third of the entire time per iteration. And for the double precision case, it's almost a factor of 1/2. So that's significant. So you can't neglect them. So it doesn't help if you make that as fast as possible. And when we looked at this, and well, basically Rob's idea was that you can, or that the reason this is so slow is that in these level 1 blast routines, you actually have to load data from memory again, which you already have loaded before in the kernel. And the idea there was to avoid this additional load by just putting these level 1 blast operations inside the kernels and do these operations on the data when you load them to do the apply or do the preconditioner. And this is basically the algorithm you get. It's still the conjugate gradient algorithm. It's completely equivalent to it, at least if there's no rounding errors. And it's basically now split up into 2 kernels. There's one kernel which is sort of organized around the around the preconditioner. So when you apply the preconditioner, you also do the residual update and you calculate some norms. And this is a good idea because here you need to, for example, here you need to load this R into memory, but you also need it here, and you need it here, and you need it here. And you only need to load it once instead of 1, 2, 3, 4 times now. And this reduces the memory access quite significantly. Then we've got another kernel which is organized around the apply method, and again you do some AXP operations there and this scalar product when you apply the operator. And again, this reduces the number of memory accesses. Okay, so now these 4 columns here is what I showed you before, and now here I basically show the same but for this interleaved operators. So the red one is the interleaved apply. So this is the apply plus all the BLAS operations that I put in there. And the blue one is the interleaved preconditioner. So it's a preconditioner plus all these other operations. So this is single precision and this is double precision. And what you see is that basically all these BLAS routines that just disappeared. They might increase these times slightly, but not really much. And this is quite a big jump from here to here, from here to here, I think. Okay, so looking at the total times, so what I did here is I basically looked at the best matrix-free code we have on the GPU. So this is the blue and bold results here, and then also the matrix-free code on the CPU, and then I compared to the matrix explicit code on the GPU and on the CPU. So these are the absolute times, but then I also show the speed up of the matrix-free GPU code relative to these other codes. So this 86 is the speed up relative to the matrix-free code on the CPU, and then this 2.1 is the speed up of the matrix-free code relative to the matrix explicit code on the GPU. And you see you get about a speed up of a factor of 2 or 3 relative to this matrix explicit code. Okay, good. So this is all I wanted to say about the single GPU implementation. As I said, we started looking at multiple GPUs. This is something that Richard Loft talked about in Exeter. So this is some work by Lin Gan from China. He worked on this Tianhe 1A supercomputer. This was, I think, last year or the year before. This was the fastest computer in the world, and it had lots of GPUs. So basically what he did is he implemented an explicit solver for the shallow water equations on a cubed sphere grid using a 13-point stencil. But really, the structure of the code is very similar to what we do in the apply function. It's also kind of a matrix vector product he has to do in his code. And what you have to do is you have to obviously do this matrix vector product on your local grid. So this is kind of one node, and then you have some halo data, and you have to exchange that halo data with the neighboring node, and do that for all the interfaces, obviously. And he did that using the entire machine, I think, so that's quite a large number of CPUs and GPUs. And the way he did it, he basically really used the GPU as an accelerator. So he split the domain. So this is one node. He split the domain up into an interior part, which is done by the GPU, and then some boundary around it, which is done by the CPU. And he basically adjusted the relative size of this and this, depending on the speed of the GPU. So obviously the GPU is faster, so this inner bit is larger than the outer bit. But he could really use both the CPU and the GPU to get the optimal performance. And the CPU obviously has to do the halo exchanges as well. So yeah, this is again taken from his talk. So here what he just shows is basically the time spent in the MPI. So that's the stuff here, which you can obviously overlap with some calculations on the CPU here. So you keep the CPU busy all the time and do some MPI communications at the same time. But you also keep the GPU busy all the time. So the GPU works on the inner bit while the CPU does the outer bit. Now, however, at some point you have to communicate between the CPU and the GPU. So this is this green bit here. And this cannot be hidden. There might be some new CUDA implementations where you can do asynchronous memory transfer, but I don't know.
You can do asynchronous memory transfer.
You can?
That's for sure, yeah.
Okay. He did do it.
Yeah.
I checked with Richard well. However, the crucial point here is you don't have to exchange the entire data, you only have to do the halos, right? So that's the same when you do like a halo exchange on the CPU cluster. And that's something we looked at. Basically, well, the idea is in our algorithm, the main conjugate gradient loop goes over the entire grid, obviously. So the time you spend in this is some timescale t times the area of the grid on the GPU. And then you have to do some host memory data transfer, and that's only given by the bandwidth and then the boundary, which is proportional to the square root of the area of the grid on the GPU. And we only looked at kind of a simple model where the GPU does the entire local block. And the question we basically ask is, how much time does this memory transfer over the PCI bus cost in relation to the total time in the loop? So that's the transfer time divided by the calculation time plus the transfer time. And that should scale like the inverse square root of the grid size, which is hopefully smaller than 1, well, obviously depending on these numbers here. So what I just did is I basically coded this up. I just do the loop here, and then I just do these halo exchanges. They're not really halo exchanges, it's just a single GPU machine. So I just copy it back and forth between the CPU and the GPU and don't do anything with it. But so if I measure these times here, so this is the problem size I varied on a logarithmic scale, and then I've got the time per iteration here, and I split this up in some total time per iteration. Then I've got the time spent in the apply and the preconditioner, which is the interleaved version, so there's no blast, so that's already in there. And then I've got some time for the halo exchange. And when you look at these slopes here, so again, this is logarithmic. When you look at the slope for the total time and for the apply, this is linear. And if you look at the slope for the halo transfer as a function of the problem size, this is a square root. And then I also plot the green one is the total time and the red one is the computation. But to make it a bit clearer, I also show these numbers here, which is basically this transfer time divided by the total time. So for relatively small grids, so 32 times 32 times 1 to 8, and there you also, I mean, this GPU runs out of steam because you don't have enough threads to keep it busy. There it flattens out, but there the transfer time is around 15% of the total time. And if you go up to 512, for example, it's only around 4%. So it's not that dramatic, but it's also not tiny. So this is single precision, double precision, similar. There, obviously, these numbers are a bit larger. So this is 5.5% for this 512 times 512 times 1 to 8 grid. Okay, I think this brings me to the end. It's just a summary of what I talked about. So we implemented this matrix-free preconditioned conjugate gradient solver for these strongly anisotropic PDEs in NWP, where we have this very good preconditioner. And we basically observed that we can get a factor of 2 to 3 improvement if we do it in this matrix-free way in comparison to the QSparse library on the GPU. Crucial was coalesced memory access and also increasing the memory throughput by interleaving these level 1 blast routines with the apply and preconditioner kernel. Did some preliminary studies of the host device halo transfer, and here's just a remark on the matrix explicit implementation. On the CPUs, it's around 2 times faster than the matrix-free implementation, so we should look at that because all the other work we've done so far on CPUs have always used this matrix-free implementation. So maybe what we want to do is some hybrid, so we want to store some data, kind of the vertical matrices, we want to store them, and then just calculate all the horizontal aspects of the operator. But obviously that depends on whether the background profile is 3-dimensional or not, whether you can do that. Okay, just a brief outlook. So what I've talked about so far is just a conjugate gradient solver. If we think about using multigrid, so at the moment on this grid, it took around 86 iterations using this conjugate gradient solver with this good preconditioner. With multigrid, we can probably bring it down to 6. I mean, that's what we've seen for this other code I wrote. So that's more than a factor of 10. And there isn't really much missing, so we only have to implement the intergrid operations. Okay, that might be a bit more complicated, but many of the ingredients are already there. For the multiple GPU stuff, we've got Eero Vainiko, who's is a professor for computer science in Estonia. He's coming to Bath in spring, and his master student is also working on this multiple GPU stuff, so hopefully we make some progress there. Okay, thank you very much.
Thanks, Anka. I think in the interest of time, we should probably call it a day there, but maybe we should thank Anka again for taking so many interruptions, and I'm sure there'll be more discussion.